Hello, my name is Kaiwen. I'm a PhD student at Penn. So in this video, I'm going to present our paper, Local Bayesian Optimization via Maximizing Probability of Descent. This is a joint work with Quan, Jacob, and Roman. In this paper, we develop a new Bayesian optimization algorithm. So the goal of Bayesian optimization is to optimize expensive to evaluate high-dimensional black box functions. And here are a few examples, including neural network parameter tuning, maximizing the reward in reinforcement learning, and parameter configuration in physics simulator. In general, Bayesian optimization is a very challenging task. So instead, we focus on local Bayesian optimization, where the goal is to find local optimum. In Bayesian optimization, the black box function is typically modeled by a Gaussian process. A nice property of Gaussian process is that the gradient is also a Gaussian process. Now that we have a model for the gradient, we can essentially do local Bayesian optimization by simulating gradient descent. So naturally, our algorithm have the following two components: learning descent directions and decreasing the objective along descent directions. Next, I'm going to show you how to pick the descent directions. We propose using the most probable descent direction. Formally, given any direction v, we define the descent probability as the probability that v is a descent direction, which essentially is the probability that the directional derivative is negative. In the following polar plot, I'm showing you the descent probability for different vectors, v1 and v2. The degree in the plot shows the angle between the direction and the x-axis. For example, 0 degree means the direction is parallel to x-axis, and the length of the vector indicates the descent probability. In particular, v1 is the direction of negative expected gradient, which has descent probability 64%. However, v2 has higher descent probability 66%. In fact, v2 is the descent direction that has the highest descent probability among all possible directions. So we call v2 the most probable descent direction. And from this example, we already noticed that the negative expected gradient may not always has the highest descent probability. So we propose using the most probable descent direction instead. Next, in this slide, I'm going to show you our acquisition function for learning the descent direction. So the idea is that we want to query points that maximize the descent probability in expectation. Suppose at some point we have the following two choices. We can either query x1, in which case the descent probability increases to 91%, or we can query x2, in which case the descent probability increases to 100%. So in this case, obviously we want to query x2 because in this case, the model has higher confidence in descending the objective. So that completes our algorithm. Our algorithm alternates between the following two steps. In the first step, we learn the descent direction such that the descent probability is high. And then in the second step, we simulate gradient descent along the most probable descent direction.
Hi, I'm Quan, and I'll be talking about the experiments we ran in order to compare our algorithm called MPD against other local optimization baselines. One of which is BBO, which is a similar local Bayesian optimization framework that minimizes the trace of the posterior covariance matrix of the GP corresponding to the gradient, and then moves along the negative expected gradient. We also tested ARS, which uses finite differencing, and then Turbo, which is a trust region-based algorithm. Here is our experiment result, which shows that our policy MPD is competitive against other baselines, especially BBO, which is our closest competitor. Our method also scales well to high dimension. Finally, to conclude, we propose a principal local Bayesian optimization framework that revolves around maximizing the probability of descending on the objective function. This includes an elegant but also easy to optimize acquisition function that approximately maximizes the descent probability. and then an update rule that move in the direction of the most probable descent, our experiments show that we outperform other local optimization baselines on a wide range of